For this problem, we want to find the volume of the part of the region below the sphere, x squared plus y squared plus z squared equals r squared, and above the plane z equals c. So first thing, let's draw a picture of what's going on here. So this sphere, I'm going to draw in sort of maybe the xz, sort of a cross section here. And so I've got a circle in xz. That circle has radius capital R. I'll write a capital R in both the x and z, and it would be the y. I guess the y would go into the screen here. And then, so that's really this x squared plus y squared plus z squared equals r squared. And then you have the z equals c. Well, that's a plane. That's z is a fixed value. Now, I'm going to draw this here. I don't actually have any constraints on the value of c here. Let's just talk a couple things about this right away here. Well, let's suppose that c is greater than or equal to capital R. That is, this blue line is sort of at the top of the sphere or above. Well, if that's the case, we can see clearly the volume. There's nothing that's both below the sphere and above the plane, so the volume is 0. If c, let's suppose c equals 0, so I get sort of the xy plane here above the xy plane below the sphere x squared plus y squared plus z squared equals r squared. Well, that's then half a sphere. So then the volume would be 1/2 the volume of a sphere of radius capital R, which would be 4/3 pi this capital R cubed, or 2/3 pi r cubed here. Now, if c was negative, that's possible. What I'm going to do is I'm going to assume, well, let's do another one before I do that. Let's suppose c is less than or equal to negative r. So somewhere down below here, if I complete my circle, there's a z is negative r. And if that blue line got below this, what I'm going to get here, so let's think about that. If that blue line got below here, I'm going to get below the sphere. Probably going to think about the top half of the sphere, and above the plane z equals c, where this would maybe drop below, I'm going to get the full sphere, although actually this doesn't really make sense when you think about it, because the phrasing says below the sphere, but if I drew a blue line, or sorry, this c like down here, it's a question of, well, I'm below this top part of the sphere, but am I below the bottom part of the sphere? What's that mean? So what I'm going to assume, sometimes I like to consider that, I'm going to assume here that c is greater than or equal to 0 here, for this sort of to make sense. And we've got anything bigger than r to be okay. We've got 0. So really what I've got left is c is somewhere between 0 and r. That is, it's going to look like this blue line here. You know, it might be scaled a little different. So we can kind of reduce this problem to that situation here. Okay, so let's go and do this. I'm going to do this first in spherical coordinates. We've got a sphere. Perhaps that seems a little bit logical. To do that, my volume, I'm going to get a triple integral. So my Jacobian is rho squared sine phi. I'm going to do this as a d rho, d theta, d phi. Theta bounds. So theta, this is going to sort of rotate around completely 0 to 2 pi. Phi bounds, well, what I'm going to do is I'm going to start at z, the positive z-axis, and then I'm going to go down in phi until I hit this intersection point. So I'm going to have to hit sort of some phi. There's sort of my biggest phi bound there. So what I'm going to do now is I'm going to draw sort of this triangle here. So when I look at this triangle, I've got a phi here. The height is c. And then this distance here, I don't know, but this here is a radius of the sphere. And so we know that phi is an inverse cosine of c over r. So our phi bounds, I'm going to start at 0, and then I'm going to get a inverse cosine of c over r. I can put those in parentheses. And lastly, I need my rho bounds. So with rho, what I'm going to do is I'm going to start at the origin with the rho. Whoops. I'm not sure what happened there. So I'm going to start at, I changed the color there. I guess we'll just do this in red now. I'm going to start at the origin. I'm going to sort of shoot out here. And none of this is in the sort of surface or the solid I care about. So the solid I care about is above the blue line. So the first time I get in the solid here is when I hit z equals c. Then I'm going to be in the solid. And then I'm going to sort of go out of the solid when I hit the sphere. So when I hit the sphere, that's really distance r from the origin. That's sort of the definition of a sphere. So the upper bound for rho is r. The lower bound is I need to get this sort of plane z equals c. So I'm going to have to do a little bit of work to do that. So what I'm going to have to do is I'm going to look for z equals c. And I want to write that in sort of to solve for what rho is in terms of phi and theta. So theta won't come into play. It'll just be phi, really. And to do that, I'm going to replace z with z in spherical coordinates, which is rho cosine phi. That equals c. And so rho is c over cosine phi, or c secant phi. So I get my lower bound of c cosine phi. And really, there's my integral. Now I just need to calculate this. So first thing I'm going to do is integrate with respect to rho. So I get 0 to cosine inverse c over r. Integral from 0 to 2 pi. When I integrate rho, well, I'm going to keep the sign phi. I'm going to get a rho cubed over 3. And that's going to go from rho equals c over cosine phi up to rho equals r. And I have d theta d phi. Kind of worried about how complicated this looks, but we'll see how it works out. It should work out nicely. Get 0 to cosine inverse c over r. Integral 0 to 2 pi. Let's see, when I plug in r, I'm going to get, sine phi times r cubed over 3. And when I plug in c over cosine phi, I'm going to get c cubed over 3 cosine cubed phi. D theta d phi. Okay. So now if I integrate with respect to theta, there's no thetas in this expression at all. So phis, really, in terms of variables. So when I integrate from 0 to 2 pi, I'm really just going to multiply by 2 pi. So I'm going to do that. I get my 2 pi. I'm also going to factor out this 3 that shows up in these two denominators, just to kind of get that out of there. So I get 2 pi over 3. And I'll have an integral from cosine inverse c over r. And what I'm left with, let's see, I have an r cubed sine phi minus c cubed. And then I have sine phi over cosine cubed phi. I'm going to write this in kind of a funny way. Sine phi over one of the cosine phis times 1 over cosine squared phi, d phi. And let's see, so we get 2 pi over 3. This is an integral 0 cosine inverse c over r. Actually, let's just, well, yeah, we'll do this. I'll just write the first one down, and then we'll evaluate this in a bit. So now this business here, what I got is sine phi over cosine phi. That's tangent phi. 1 over cosine squared phi. That's secant squared phi. Now what's nice about that here is that the derivative of tangent is secant squared, so I can do a u equals tangent phi, and this will just give me then tangent squared phi over 2 when I integrate. So maybe we'll do this off to the side just to show what's going on. I'm going to integrate tangent phi times secant squared phi, d phi. I'm letting u be tangent phi. Then du is secant squared phi, d phi. And so my integral, let's see, it's u times du. And so I get u squared over 2 plus c, but it's a definite integral eventually, so I don't care about that. And so I get tangent squared phi over 2. You get sort of good enough at that, you might be able to skip through and just recognize this as tangent squared phi over 2 once you do the antiderivative. In any case, what I get is 2 pi over 3. So I have r cubed. Antiderivative of sine phi is negative cosine phi minus c cubed times tangent squared phi over 2. And then I have to evaluate this from phi equals 0 up to phi equals cosine inverse c over r. Okay. So I get my 2 pi over 3. I have my negative r cubed. Cosine of cosine inverse c over r, well, phi is somewhere between we're dealing with angles between 0 and pi over 2. We don't have to worry about any negatives or translations or anything like that. So cosine of cosine inverse is really just going to be c over r times that, minus, we have c cubed over 2, and then we have the tangent squared phi squared. So tangent of cosine inverse c over r. Well, our triangle here, this is phi. This third side, or third leg here, what that's going to be is square root r squared minus c squared. So this side over here is a c, just by the Pythagorean theorem. And so tangent of this angle, whose cosine is c over r, is going to be square root r squared minus c squared over c. So what I'm going to get is square root r squared minus c squared over c, and that whole thing is squared. So this is just the tangent of the angle that gives us a cosine of c over r. So the angle that gives us cosine c over r is this phi. That has to have a tangent of opposite over adjacent, which is square root r squared minus c squared over c squared. So that's when we plugged in phi equals cosine inverse c over r. We plug in 0. Let's see, cosine of 0 is 1, so I'll get a minus, which will turn into a plus. R cubed times 1 is r cubed. Tangent of 0 is sine 0 over cosine 0. That's 0 over 1. That's just 0, so I don't really need that term when phi equals 0 for the tangent squared part. Okay, so now we just need to work on this a little bit. So I get 2 pi over 3. I have a, let's say I can get a negative c times r squared. So the r cubed, I cancel one of these r's with the r in the bottom. I get a c r cubed. I'm going to get a minus, let's see, it's going to be c cubed over 2. When I square this, get r squared minus c squared over c squared plus r cubed. So I end up with 2 pi over 3 negative c r squared. Let's see, when I multiply through the c squared, cancel with 2 of the c cubes, leave a c on top. So I'm going to get minus c r squared over 2, and then plus c cubed over 2 plus r cubed. So this is going to work out to be 2 pi over 3 times, let's see, negative cr squared minus half cr squared. That's minus 3 halves cr squared plus c cubed over 2 plus r cubed. Probably a nice form of that would be to multiply the inside by 2 here and divide the outside by 2. Or just take this 2 out here and multiply that through. So what I'm going to get is pi over 3 times, when I multiply 3 by the 2, I'm going to reorder this to put the r cubed first. So I'll get 2r cubed, and then the c cubed plus c cubed. The 2 will cancel the denominator, and then minus 3cr squared. So there is my answer for the volume of this region above the plane z equals c. Now, one thing I should check here is, does this fit our end cases? So our end cases, this is when c equals 0, I'm expecting to get 2/3 pi r cubed. And when c equals r, I'm expecting to get 0. So if you plugged in a 0 for c, you'd get 2r cubed times pi over 3. That's really the formula we want. This term will be 0. That term will be 0. That works out. If you plug in a capital R for c, you'll get 2r cubed plus another r cubed is 3r cubed minus 3r cubed. You will get the 0. So at least the endpoints work out. Gives us some sense that maybe this is right. Okay, so that was spherical coordinates. Let's try this integral in cylindrical coordinates as well. Let's go back and maybe draw the picture again. What we've got is we've got a circle, really radius capital R, and then there's some sort of plane z equals c. So this is a z-axis and maybe an x or a y, depending on how I want to think about that, or maybe a lowercase r for radius in cylindrical. And what I'm going to think about now is sort of the shadow of this. So if I sort of had, I don't know, a bunch of water falling from the top straight down, the shadow would be sort of hit all this stuff down here. It'd really be just this range here, which in the xy plane is actually going to be a circle. So remember, this is sort of a circle here. And so what I'm going to get as my shadow is really a circle here. Now the radius of that circle is really what we want to know, and that's when z equals c, and we're on the sphere. So we have to satisfy x squared plus y squared plus z squared equals capital R squared, but also z equals c. So we want to find sort of the radius of this. Well, x squared plus y squared, that's lowercase r squared. Z squared, that's going to be c squared. That's capital R squared. And so r, little r, is going to be square root of capital R squared minus c squared. So our radius here, this sort of end point here, this is going to be these square roots. Really, I suppose plus or minus these. We have the positive square root and the negative square root. So that tells us that this radius here is square root capital R squared minus c squared. Okay, so what we need to do then, our integral, our volume, we're going to get a triple integral. When we do a cylindrical volume, volume means integrate the function 1, but we get our Jacobian, which is r. And then let's do this, maybe a dz, dr, d theta. So theta, we're going to rotate completely around, is 0 to 2 pi. R is going to go from 0 out to this square root r squared minus c squared. So it looks like there's some variables in there, but they're really constants here, just unspecified constants. So there's no z's is the key thing. And then z, when we think about z's height, is going to start at, well, this z equals c, and it's going to go up to really the sphere. So what we're going to do is we're going to start at z equals c. We're going to go up to the sphere, so we have to sort of give the height of the sphere in terms of the radius or theta. Again, theta won't come into play. And so what I'm going to do is take my sphere equation up here, x squared plus y squared plus z squared equals capital R squared. Solve that for z. Maybe before I do that, let's do x squared plus y squared is lowercase r squared. This is going to look very much like solving for r. Z squared is capital R squared minus lowercase r squared. That is, z is plus or minus the square root of capital R squared minus lowercase r squared. Now the negative square root would be sort of the bottom half of the sphere. We're not going to worry about that. Well, we could say, actually, no, it wouldn't be the bottom of the sphere. We know from our assumptions that z is positive. If we're worried about negative z, then we'd have to think about that too. So we really don't need the plus or minus. This is just z equals square root r squared minus capital R squared minus lowercase r squared. So we get a square root r squared minus r squared, but different r's. Okay, now we can evaluate this. So you can integral from 0 to 2 pi, integral from 0 to square root of capital R squared minus c squared. And when I integrate with respect to z, I'm going to get rz from z equals c up to z equals square root capital R squared minus lowercase r squared. I'm going to do dr d theta. So that will give me integral from 0 to 2 pi, integral from 0 to square root capital R squared minus c squared. Let's see, this is going to be r times square root capital R squared minus lowercase r squared minus r times c, dr d theta. What I can do now is I can integrate capital R squared minus r squared, square root of this, times r by letting u, whoops, didn't get the color I want there. So I can let u be this capital R squared minus lowercase r squared. So u equals capital R squared minus lowercase r squared. Du is negative 2r dr. So I have my dr, I have this r, I need a negative 2. So what I'll get is a negative 1/2 to be able to put the negative 2 there. And then I'm going to get r squared minus r squared, capital minus lower, to the square root's 1/2. I go to the 3/2, and then I divide by 3/2 here. So that's this first antiderivative. The second one is much simpler. It's just c times r squared over 2. Just integrate r, c is a constant. So I do this from r equals 0 to r equals square root r squared minus c squared. And I have a d theta when I do this. And what I'm going to get, let's say I get an integral from 0 to 2 pi. And when I plug in capital or square root r squared minus c squared for lowercase r squared. I'll get rid of the square root with the square. So I'll get capital R squared minus c squared. That's just going to give me a c squared in here. And when you use c squared to the 3/2, that'll be a c cubed. So I get minus 1/2. This 3/2 will get multiplied by a 2/3. And then I'm left with a c cubed on the top. Minus c, this square root is going to be capital R squared minus c squared all over 2. And then I plug in the 0, I'm going to get a plus, let's see, this 1/2 and 2/3, those will cancel, so it'll be plus 1/3. When you plug in r equals 0, you just get capital R squared. Square root will give us just r, and then to the third will be a 1/3 capital R cubed. So you get all that. When I plug in r equals 0 to the second term, I just get 0, d theta. Now, all the d theta is going to do, or the integration with respect to theta, there's no thetas left. So that, again, is just going to multiply by 2 pi. So what I'm going to get is 2 pi times this thing in here. So we can simplify this a little bit. These 2's cancel. We have negative c cubed over 3 minus c r squared over 2, and then plus c cubed over 2 plus 1/3 capital R cubed. So we get this formula. Now this should be the same as what we had before. So let's see if we can make it look the same. Let's look at what we had before. So we got this pi over 3 times 2r cubed plus c cubed minus 3c r squared. So let's change this. Let's do this as a pi over 3. If we do that, I divided by 3 here. So I need to multiply by 3 on the inside. I also have the 2 needs to go in, so I'm going to multiply by 6 on the inside. So when I do that, what I'm going to get, when I multiply by 6, I'm going to get a negative 2 c cubed. I'll get a minus 3 cr squared plus 3 c cubed. And then what I'll get is a plus 2 r cubed. And so when all is said and done, I get pi over 3. Let's say I have the 2r cubed. I have a 3c cubed minus 2c cubed. That's plus c cubed. And then I have a minus 3cr squared. So 2r cubed plus c cubed minus 3cr squared with the pi over 3 out in front. And that matches what we had before. So again, it's an example of a problem where you can do in both spherical and cylindrical coordinates. This one, maybe spherical is a little bit easier. They're somewhat the same, a little bit different. I probably would go with spherical here just because of the sphere. That z equals c bothers me a little bit in spherical, but once I get used to it, that's not that bad to do the substitution here where you set, let's see, z equal to c and then rho cosine phi equals c and solve for rho. It's not that bad. Integrals worked out okay. So you can kind of pick what you want to do here.